In general, modern industrial manufacturing systems benefit from wireless communication systems, especially in terms of enabling flexible adaptations to changing manufacturing parameters. Many different devices, machines, and systems need to communicate with each other. Sensor data streams, for example, need high data rates, control systems of CNC machines need ultra-fast response times, and autonomous vehicles need different parameters. 5G is not yet flexible enough to handle this variety. Every adoption is time-consuming and can generate errors. Our approach for 6G networks is designed to change this, automatic adaptations instead of manual configurations. And this is why we are developing the so-called networks in networks concept, specialized subnetworks for different applications. A network for CNC machine control with ultra-low latency and in parallel a high data rate network for sensors.
Together we have developed a system that adaptively allocates frequencies so that there are no more conflicts. Our solution can react completely autonomously to changes caused by moving on newly added subnetworks. This dynamic spectrum management allows efficient operation and management of networks in networks in future 6G infrastructures. For our solution, subnetworks connect to the local 6G infrastructure and are then coordinated by it. A local spectrum manager dynamically distributes the available spectrum to the currently active subnetworks and adjusts the allocation accordingly in the event of changes. To enable this coordination autonomously, communication between the subnetworks and the spectrum manager through the local 6G infrastructure must be ensured. For this we use the routing architecture Kira, which is especially designed for large and highly dynamic 6G infrastructures and provides robust connectivity between all components. As soon as a new subnetwork connects, Kira provides it with connectivity to all other components. The subnetwork then uses Kira to search for the local spectrum manager and registers with it. The spectrum manager then calculates the optimal frequency allocation in the new situation and communicates this to all participating subnetworks. With increasing number of subnetworks, these calculations become very computationally intensive. Therefore, we also have investigated the extent to which an AI solution can help us here.
With the integration of network in networks, the operation of the networks becomes more complicated, especially if the subnetworks also adapt to their respective environmental conditions. AI could support the operation of such networks, for example, by assigning frequency bands to the subnetworks, or at a lower network level by configuring network parameters. For example, here in our scenario, to control the communication between the base station and AGV. For example, by using a reinforcement learning agent, we can continuously change the network configuration to ensure a fixed data rate for communication, while at the same time we are minimizing transmission power to generate less interference and also to become more energy efficient. For example, we see here that when the AGV moves away from the base station, the transmission power increases, and when the AGV approaches again, the transmission power decreases.
Independent if we want to use AI to manage the network operation, or whether we want to use the network to connect an AI application with the end user, we need to think about where we want to train the AI models and where we want to infer. The placement typically depends on the requirements on the AI service, for example, latency constraints, but also on the devices that collect the data, because for AI we typically want specific hardware. We therefore need to understand how network conditions and data distribution will affect an AI service. Testing in real environments is often not possible. Instead, we created an emulation network called ContainerNet that allows us to train and infer machine learning models and reinforcement learning agents in different network condition scenarios and also with different data distributions. So in this demonstrator, we show how we can use ContainerNet to actually emulate industrial environments, for example, a backbone network, to train a machine learning model in such a backbone network without actually having the real network.
The approaches developed in the Open6G Hub will make it possible in the future to use existing limited spectrum efficiently for a wide range of industrial applications. Using DSM and Kira, as well as the use of AI, 6G NINs can be configured fully automatically without the need of manual input. The seamless integration of the subnets into the overlaying wireless networks ensures a continuous flow of data and information. The benefit of this approach is that it provides an efficient solution for a variety of applications, for example in the industrial sector, and the realization of the future factory.